Should Okay, why don't we get started? Can you hear me okay? All right, good. So my name is Dr. Ponacholi. I'm one of 3 instructors for the course. The course coordinator is Dr. Mary Taub. So if you have any issues dealing with the course as opposed to a particular section, you should contact her. First and foremost, UB Learns. How many of you have already been there to look for information on the course? All right, good. Everything is going to be there. All right, there's under course information, Dr. Taub has put some general policies, but I'm putting all my stuff in the course documents. So go there, you'll see what you need to see. I'll go over that in a second. So the course has 3 lectures split into thirds. I'm going to do the first section, then Dr. Wilski will do metabolism, Dr. Taub will come in for gene expression. The text, Matthews and Van Hold, we're using the 4th edition, but it's essentially identical to the 3rd. So I'll give you references to both texts. Okay, so we meet 4 days a week in here, 9 to 9:50. Recitation historically has been my office hours. I haven't taught this for 10 years, this class, so I'm back. So, bless you. It's my understanding that with so many people, finding a convenient time where you could all attend is kind of difficult. So my rationale was, if we're here Monday, Tuesday, Thursday, Friday at 9, you most likely don't have something at 9 on Wednesday. Is that true or untrue? Mostly true. Okay. So starting this week, recitation will be over in Farber Hall 144, 9 to 9:50. What we're going to do there is go over the problem sets, which I will post, the problem set answers, and any questions you have regarding lecture material. So for this Wednesday, we will meet, and we would have only had 2 lectures, so if you have questions on lectures 1 or 2, we can address that. As things develop, if I get contacted by a number of you that say that you're having problems making it at 9, I can try to add an office hours up in my office, but if we can avoid that, then let's try to avoid it. All right, but I'll be accessible to you if you need the help. Exams and the keys to the exams will be posted outside 140 Farber in the glass cabinets. That's the departmental office. The exam answers, keys will not be posted on UB Learns. You're going to have to go, excuse me, to 140 Farber to look at them. All right, so what is on UB Learns? The lecture notes, I'm speaking for myself. I'm not sure about the other instructors right now. My lecture notes will be there. I'm still kind of going back and forth as to whether or not to give you my PowerPoints, with the rationale being that the course is video recorded. So I'm going to try to encourage you to come to class and actually see the PowerPoints firsthand. If there are some things in the PowerPoints that I go over that are really important that I've omitted from the lecture notes, then I may put the PowerPoints up after the fact. Okay? So the link to the video recordings is on UB Learns. The problem sets, I'll post the first one probably today or tomorrow, and the problem set answers will go up, but after we've had a chance to talk about them in recitation. I don't want you to be too tempted to look at the problem sets and run into a problem and then just sneak and look at the answer. Right? It's better for you to try to work them out. The problem sets are very similar to the questions that you're going to see on the exams. And in some cases, they're old exam questions. So you really want to focus in on those. Anytime you have a question, just stop me in my tracks, all right? Don't worry about it. Just don't fall down the stairs. All right. So the exams. There are 6 exams during the semester. There'll be 2 exams for each instructor, and leading up to the exam, you'll have your recitations, office hours, and we will schedule an extra review session prior to every exam to try to, find a convenient time to make sure that we can get everybody in and give them an opportunity to get things clarified. Makeup exams, all right? You cannot do it unless you have a medical emergency, which, and this is all in Dr. Cobb's notes, I'm just reiterating it for you to clarify it. If you get sick, you have to notify the instructor within 24 hours, and you have to provide a doctor's note. If you, before the fact, look and see when there is an exam and there is no chance that you can make that, all right? You have some unavoidable conflict, then at least 5 days in advance, you have to let that instructor know, all right? The exam questions, as I said, they are not going to be posted on the UB Learns, so they're confidential. So when you take the exams, you'll have the exam, you'll have an answer sheet. It may be, it will be a bubble sheet. It may or may not have some short answer in there. You will be able to take the cover of the exam out if you want to write down the answers that you put so you can remember them, but the exam itself you will turn back in, as well as turning in your grading sheet. You don't want to forget that. And then when the exam's been graded, you can take what notes you've made of what answers you had, look at the exam. If you have any issues with what we are saying or what I am saying the correct answer is, then within 1 week you have to write to me and say, I think you're full of it because this question is full of it. And then we'll go from there. Okay, so contact for me. I'm up in the Biomedical Research Building on the 6th floor. I'm in room 649. And you can email me at any time, and like I said, if it turns out that there's a handful of you that really need a little bit more help, there is a TA that I have to speak with and find out how proficient they are on all of these things. Generally, I like to do it because even though the TA can be helpful, I don't want situations to create where maybe you heard something from the TA that is a little bit opposed to what I told you. So to try to keep things clear and consistent, I will try to be accessible to you as much as possible, all right? So if you have trouble, just send me an email. Okay. Any questions so far about format, policies, anything? All right, so for this first section, there is a very strong overriding theme, and that's the relationship between structure and function. So at all times when we're going through everything on, small details as things grow to bigger and bigger systems and interactions, you always want to think about that, all right? Structure, function, those 2 words should just be ringing in your head the whole time, because it's the structure of things that in fact dictate their function. So we're going to be going over that on various levels, but that's something that you should just keep in mind all the time. So some of the initial questions are, we have, let's say, the building blocks of macromolecular assemblies, the macromolecules themselves, so we want to look at those structures. see what they tell us about what those molecules might be capable of doing with these macromolecular assemblies where you have multiple molecules coming together. How is it that they come together? What are the chemical and structural properties that are dictating these assemblies? And then once they are assembled, let's say a protein, what is it about its structure that has properties that are going to facilitate or allow for that protein to function in its role in the cell. All right, so over the next 15 lectures, just look at what we're talking about and think about, all right, what is the structure-function relationship in what we're talking about? Okay, so each day when you come in, this is what you will see. I'll have an outline for you. So technically, this is the beginning of lecture 1 with respect to specific information other than concepts. So readings, 3rd, 4th edition will be there. So what we're going to go over for the rest of today is just a brief review of thermodynamics to bring most people up to speed. And if you have problems, again, the problem sets will help you, and feel free to email me. So we'll go over some basic concepts of thermodynamics. When we talk about biochemistry, it's the chemistry of the cell, and the cell is mostly water, so we have to know something about the structure of water and its properties, since it is the medium that all of this stuff is happening in. And at the end of today, we'll talk about the hydrophobic effect. Okay, so to start out, structure and function. The first section of the course, the examples that we're going to look at in terms of structure and function is going to deal with proteins and membranes. All right, but you should not lose sight of the fact that the same concepts with regard to structure and function apply also to nucleic acids, which we are not going to talk about in this section, all right? But when we look at the building blocks, the monomers that are then going to assemble into these higher structures, we have amino acids, lipids and phospholipids, and nucleotides. So the first thing that we would want to do is to look at these monomeric structures and appreciate what their structure is and what the properties are of those monomers that are going to allow them to do things when they come together. How do these structures give rise to some biologically important properties? We'll then look at the assemblies of these monomers into the higher order macromolecular structures. So amino acids comprise proteins, lipids to membranes, nucleotides to DNA and RNA. All right? And in there, we're going to look really at kind of two questions. One is we have these monomeric structures that have certain properties. So when they're going to come together, we want to understand how their structures allow for stable higher order structures to form. So when they come together, right, you have to have some stability being imparted to those molecules so that they will retain their structure. So we want to understand the structure function. We want to understand the structure of the monomers, how it allows for higher order assembly. And then once we have a higher order structure, what the structure of that molecule tells us about what type of function it can have. All right, so at any level where we're looking at, let's say, simple molecules, higher order structures, you always want to think about that relationship between structure and function. Okay, so ultimately, we have building blocks that are moving up to give us proteins and membranes. So when we finally get to those higher order structures, we're going to look at the proteins and try to understand how that folded protein carries out its function. Or we'll actually look at the molecular structure and understand how that is perfectly suited to do what that protein has to do in terms of maybe grabbing the substrate and acting on it. All right? It's going to have a structure which is compatible with grabbing onto its substrate. It's going to have an active site that's going to carry out some chemistry. And things don't just happen in a black box for no reason. They come together, they stabilize, they interact. There's chemistry that goes on, and the only thing that can really cause that to happen are proper structures and molecular interactions. The same for a membrane. Membrane is separating two aqueous environments. So in a cell, the internal of the cell, the inside of the cell, the outside of the cell, right? But it cannot be an impermeable barrier. There's stuff, information, small molecules, everything that has to traverse that membrane. So we're going to talk about the structure of the membranes, but also the proteins that reside within the membrane to make it selectively permeable to either information or transport, right? Critical point, again, the three-dimensional structure. How does that relate to function? All right, any questions so far? Okay, so this basic truth, all physical and chemical processes are driven by energy changes, right? Not only do things not happen in a black box, but there's no free lunch, right? The energetics have to be there. You have to ultimately have things being favorable energetically. So we want to go over a brief review of thermodynamics to understand what things contribute to making reactions go forward so that they are energetically favorable and they will take place. All right, so let's start out with some bimolecular reaction. You have reactants A and B going to products C and D. Some basic terms, we can define an equilibrium constant. So the equilibrium constant is where there's no net reaction. At the end of the reaction where it has come to equilibrium, that equilibrium constant is a ratio of the concentration of the two products, right, multiplied to each other over the concentration of the remaining reactant A times reactant B, all right? The second term that we need to talk about is the Gibbs free energy change, or delta G. How many, when I say delta G, how many of you out there hear a bell that you've heard this before? Most of you, hopefully, okay. So delta G is the driving force for the reaction. It's telling you the energy change that is happening during the reaction. And actually, before I talk about this term, let's look down here, all right? So it's expressing the driving force for this reaction. If delta G is less than 0, right, that means in going from reactants to products, right, the free energy change is negative. So you're going downhill energetically, and this will occur spontaneously in the forward direction, right? It's telling you, yes, this reaction will go forward if you just sit back and watch it. It doesn't tell you anything about how fast it's going to go, right? There's a difference between the thermodynamics, which is telling you how favorable the reaction is in principle, as opposed to how quickly it gets to equilibrium, right? We'll go over that point again when we get into kinetics. But when you just look at the energy diagrams and you say, are these things going to do anything if you don't tickle them some way? If the delta G is negative, then it will go forward spontaneously. When delta G equals 0, there's no net reaction. That means it is at equilibrium. And if the delta G is positive, right, then that reaction will not proceed spontaneously. So I'm going to say it now and say it again and again. When you look at a delta G as being positive, on the face of it, you would say, is this reaction going to take place? The question is it going to take place spontaneously? And the answer would be no. But you shouldn't extract from that the reaction is not going to occur, because in biological systems, there are a lot of things that are energetically unfavorable, but you couple them to reactions that are favorable, all right? So when we talk about delta G, we can talk about the delta G of a particular reaction that says, you know, that ain't going to go anywhere on its own. But if you take another reaction and couple to it, like the hydrolysis of ATP, which you will get into, that's energetically favorable, when now you look at the system, you say, are things going to go forward? The answer is yes. So we don't, in a biological system or a process, if we just stood back and say, well, delta G is positive, nothing's going to happen, so why are we even talking about it? It's an imaginary reaction. It's not. The energetics of this reaction here might not be favorable, but when you couple it to other processes where the energetics are favorable, then the overall net energetics are favorable and things will happen, okay? So what is it that contributes to these reactions? There are two components, enthalpy and entropy. So enthalpy, delta H, we're dealing with heat, all right? So if delta H is negative, then when you look at this equation, if we want delta G to be negative for things to be favorable, then delta H you would want to be negative, and that's true. Delta S is your entropy change. So if we would like this term minus T delta S to be negative, then delta S would be what? Positive or negative? Positive, which is an increase in entropy, an increase in disorder. So that's what we want, bless you. So when you think about it, when you look at, let's say, things going on in a cell, you have all these monomers, and then they're coming together to form a higher order structure. Would that higher order structure be more ordered or less ordered with respect to the building blocks? It's more ordered. You've created something. So when you look at that and you say, well, this doesn't make sense. The universe is just dissolving away. Entropy is increasing. That's what we want. What it is it's the coupling that we're talking about. All of your bodies here, if we stop feeding energy in, what's going to happen? You're going to decompose. Your entropy is going to increase, and it'll get smelly in here, but that's the natural way of things. You're fighting off entropy, so you're bringing in energy, converting it into useful ways to couple it to reactions to maintain the order of your structures. All right, so that is a snippet of realization on how you're dealing with systems, not a reaction by itself. Am I going to maintain my sanity and my structure and not decompose spontaneously? Yes, but you have to couple it to things that are going to provide the energy to do that. Okay? All right, so here's some examples. We can have, for the free energy changes of things to occur, we can have enthalpy contributing or entropy contributing, or both. So here's an example. You have a process that's driven strictly by entropy. So let's say we start out with a salt solution or a sugar solution, and we overlay it with pure water. After a certain amount of time, these molecules have redistributed, right? That driving force for that is of simple diffusion is entropy, right? You're increasing entropy by giving this concentrated solution extra water for diffusion. That's a simple process. All right, so let's look. Here's an example of a reaction where both enthalpy and entropy are contributing favorably to the reaction going on. So if we have glucose fermenting to ethanol, which, well, I won't say it. I would, but the recordings are taped now, so I got to be careful what I say. All right. So with delta H, that is a negative term, right? So that is going to be favorable. We also have minus T delta S being negative. And if you look at it, you can see that delta S then is positive, which is an increase in disorder. And you can actually look up here and say, well, if you have a solid which is going to a liquid and a gas, which side of that equation is more disordered? The right side, okay? And so your overall delta G is a large negative, all right? Some reactions may be driven only by enthalpy or only by entropy, but again, when you look at the overall net, if the delta G is negative, then it's a favorable reaction. So here's combustion of ethanol, right? You get a tremendous amount of heat being released. Your minus T delta S is slightly positive, but here you have an overall delta G which is negative, right? When you look here, you've got 3 molecules of oxygen, which is a gas, and a liquid, but you're now getting 3 molecules of a liquid over here, liquid being more ordered than a gas, all right? But basically, this reaction is being driven only by enthalpy. This reaction, decomposition of nitrogen pentoxide, is driven solely by entropy changes, where you have a solid which is going to 2 gases. So your delta H is very positive, all right? That's not favorable in terms of enthalpy, but in terms of entropy, you have a very large delta S which is positive. That term then becomes minus T delta S is negative, and you have a delta G which is slightly negative, but it will occur spontaneously. Again, the delta G's are only telling you whether or not the reaction is favorable to go in the forward direction spontaneously without tweaking it at all, but it doesn't tell you how quickly it's going to occur. Okay, so not surprisingly, the equilibrium constant is in fact related to delta G. So what we do for a given reaction is we define a term which is called delta G0, which is the standard state free energy change. So when you want to compare different reactions and say what are the intrinsic differences between these reactions moving forward, we have to assay them under some standard conditions. So what is done is if you had your reactants and products and you take each one at a concentration of 1 molar and you put them all together at 25 degrees centigrade, you then sit back and look at the energy change that occurs as that is going to equilibrium, right? It's not just the reactants, it's the reactants and the products. So that gives us a standard set of conditions that we can look at different reactions, and then mathematically, this delta G0 is in fact related to the equilibrium constant, minus RT, the natural log of the equilibrium constant, all right? So most of the time we will talk in terms of delta G, but the delta G0, you need to know that this is kind of a situation where we can define what the conditions are for 2 different reactions to be able to compare them more directly, all right? So, okay. So, I remember. So I've already touched upon this, right? When we're talking about delta G, when we're looking at processes that comprise multiple things going on, we have to look at the free energy change of the complete system. We're going to look at one example of that in a minute here, dealing with the hydrophobic effect, right? Both delta H and delta S usually contribute, and I've told you that you have to remember the distinction between thermodynamics and kinetics. Thermodynamics are telling you intrinsic energies between reactants and products that are acting as driving forces, but something can be very favorable to occur spontaneously, but it doesn't necessarily mean that it's going to get there quickly. Why? When we say it's favorable energetically, we just said that the delta G is related to the equilibrium constant, right? The equilibrium constant is what? It's a ratio, right, of the product of the two products concentrations at equilibrium over the reactants. So that ratio just tells you whenever you get to equilibrium, these are the ratios. That is the equilibrium constant. That's related to delta G. But if you then say how quickly is the reaction going to get to equilibrium, that's different, all right? And we will talk about that in kinetics. So we will look at multiple examples of delta H, delta S, their contributions to delta G in terms of allowing chemical reactions to take place, protein folding, membrane assembly, the association of enzymes with their substrates, right? It's not, I could say it's not rocket science. I mean, there's information that you obviously need to know, but, you know, there's no free lunch, and things don't happen in a vacuum. So when you look at biochemistry and you say, well, what the heck is going on and why, you'd say, well, if you look at the characters, this is what they look like. A lock and a key. If you've got a lock and a key that doesn't fit it, nothing's going to happen. So you have to have things that structurally are compatible and they can come together. But then energetically, there's no free lunch. You can't squeeze blood out of a turnip. You can't force things to do things that are energetically unfavorable. The universe tells you you can't do that. So when you look, when we talk about structure and function, you will see how the structure of things even allows for the things to come together in an energetically favorable way. All right? And we'll see one example of that in a minute. Okay? All right, any questions before we? Okay. So I already told you that most biochemistry is aqueous, and because things cannot work in a vacuum in biochemical systems, you have your proteins and membranes are interacting with water. So whatever they're doing or whatever they're disallowed from doing, it's going to have something to do with the energetics of how they're interacting with water, all right? So we should start and take a look at water. And again, this is the most simple example, right? When we talk about structure and function in biochemical systems, what is the most simple biological molecule that we would probably look at? It would be water. And water is a good example. When you look at it and you look at its structure and you understand it, then you can say, now I understand how structure is dictating function. The properties of water stem directly from its structure, right? So what do we know about water, right? It has a high viscosity, a high boiling point. You have to put a lot of heat into it to turn it into a vapor. So it basically tells you that there is association of these molecules, right? They don't really like to be disrupted that much. You've got to put a lot of energy in there to get them spinning around and turn into a gas. So because you have to do that, before you have to provide a lot of energy in to raise the temperature and ultimately raise it to the point where it vaporizes, it's going to stay liquid over a large temperature range, which makes it a good solvent, all right? So what is it about the structure of water? How many know that water is referred to as H2O? How many don't know that? Okay. So there are two things about water, its structure, that we need to think about. First of all, it's not a linear molecule, it's a bent molecule. All right? It's about 104.5 degrees. The second is when we think about oxygen, hydrogen, and electrons, what do you know about oxygen? It's an electronegative atom. It wants to draw electrons toward it to fill its outer orbital. So Because of that, you have electrons being drawn toward the oxygen, so you actually have an asymmetry in the molecule in terms of charge, right? You don't have a full-blown negative charge on the oxygen, but when you look at it with these electrons being pulled, you actually have a tetrahedral structure where the two protons are slightly positively charged, right? They don't have a full-blown positive charge, right? They're delta positive, right? They're positive light. They have an electron deficiency because the oxygen that they're bonded to is pulling the electrons towards it. Consequently, you have two lone pairs of electrons on the oxygen, which is going to give you slight negative charge. So when you look at the water molecule, what you really should think of it as is a tetrahedron, right? Everyone knows what that is? And in the four corners of the tetrahedron, you have two slight positive charges and two slight negative charges. If the molecule was linear, right, you would not have what you have with the bent structure, which is called a dipole moment, right? So when you look at this structure, let's say the top, the ears of the Mickey Mouse oxygen are slightly positive and slightly negative, excuse me, and down here slightly positive. So if we looked at the molecule this way, kind of head on, we could say that it's more negative towards the top of the oxygen and more positive down here, right? But if we look more three-dimensionally, we see these slight negative and slight positive charges in the four corners of the tetrahedron. So that is the structure. What are the properties that stem from that structure? The important thing regarding water is when two molecules come together, we have what's called a hydrogen bond, all right? So a hydrogen bond is an electrostatic interaction. It's not a covalent bond. It's not where two atoms are equally sharing, right, electrons. This hydrogen bond is due to an electrostatic interaction. When we talk about electrostatic interactions, we're talking about charges. So what is it that's making this a favorable interaction in terms of enthalpy? Here you've got one of these corners which is slightly negatively charged, and negative charge likes positive charge, and the hydrogen atom here is slightly positively charged because it's hooked up to the oxygen in its molecule, pulling electrons away, all right? So this hydrogen bond is very, very important, not just for water, but for stabilizing a lot of structures in biochemistry. We'll go over that numerous times, all right? So we have water, and what do we know about water? We know that you have hydrogen bonding going on between water molecules. If we then add something to water, let's say we want something that's going to interact well with water. It's going to dissolve. What would that substance have to do with water? It would want a hydrogen bond or electrostatically interact. So when you have salt and you put in sodium chloride and you have a positively charged sodium atom and a negatively charged chloride atom, right? That positive charge of the sodium is going to interact with the water, but what, if you look with, keen eyes, where is that sodium going to be interacting? It's going to be nuzzling up to what atom? The oxygen, okay? And the chloride, the hydrogens. So that's what we call hydrophilic molecules. Hydrophilic molecules are molecules that have some charge to them. You put them into water, and because they have charge, they can interact favorably electrostatically with the water, which is essentially composed of all these molecules that have slight positive and negative charges. What's a hydrophobic molecule? Something that can't hydrogen bond, like oil, right? And the reason that oil does not interact favorably with water is it doesn't have any charge, right? You have carbon and hydrogen, and the carbon's not very electronegative, so you're not getting any asymmetries there, right? We'll talk more about this, but suffice it to say that the hydrogen bonding is very important for water and its properties, but also for stabilizing structures. Do you have a question?
What do you mean by favorable?
A favorable enthalpy is where when two things come together, there's actually a slight release of heat. Okay? So when you look at two things coming together intuitively, you say a positive and negative coming together, right? There's no entropy, right, that is favorable, let's say, for them interacting, but electrostatically, the positive and negative charges give you a favorable enthalpy. Okay, so just to gain an appreciation of water in terms of why is it acting the way it's acting, I've shown you here a hydrogen bond, but each water molecule has how many positions on it that could engage in hydrogen bonds? 4, right? 1, 2, 3, 4. So I've shown you a hydrogen bond here between two water molecules. Now I'm going to say, well, let's look at this water molecule. That water molecule can interact with how many other water molecules? 4, right? This water molecule is going to interact with how many? So when each water molecule can interact with 4 other water molecules and they're doing it, can you envision how that's giving some structure to water, right? In the extreme case where it freezes into a lattice, you have all those molecules locked into place through the hydrogen bonds. But in water, it's like you're at a county fair and there's a big dance going on and there's 1 million people there, and at any one point in time you're dancing with 4 people, and then you're turning and dancing with another 4 people and turning and dancing with 4 people, and they're all doing the same thing. Everybody's spinning around, but there's some order to it, right? Because of all those interactions, that's why water, if you want to drive it away as a gas, you have to put in a lot of energy, because it's got all of these hydrogen bonds maintaining this dynamic structure, right, of this wild dance going on between the water molecules, okay? So, hydrophobic effect, we got 5 minutes. So I asked you, if we take something that can hydrogen bond or interact with water in a favorable way electrostatically, it's hydrophilic. If we put something in which really doesn't have any charge to it, it doesn't, right? It doesn't interact favorably with water. So these nonpolar molecules, if you start putting them into water, what's going to happen? They're taking up space. So it's almost like in the dance that we're talking about. Everyone's dancing on this big dance floor. And you want to continue to dance with 4 other partners all the time, but let's say it really is oil, and you put a circle of oil on the dance floor and nobody wants to stand on it, right? You can't be in that position. It's an unfavorable position. So to do your dancing, right, you start becoming more limited in the places that you can go, right? There's another example of this that's here. So all of these water molecules, right, are spinning around and they're being very promiscuous and they're dancing, and no problems, but then you start putting in more and more of something which is not going to participate in the dancing, right? They're social misfits or whatever. They're not going to get into it. And as you start putting more and more, right, these water molecules here are starting to get stressed out, okay, because normally they're free, right? Long flowers in the hair, they're free, they're spinning around, they're dancing, everything is fine, and then these social misfits start coming in, and they turn to dance, and they're just sitting there saying, So then they have to turn somewhere else to find a favorable partner. And as more and more of these invaders come in, the water molecules are getting more and more stressed out because now they're looking over here, no, can't dance with that person. Look over here, no, can't dance with that person. Look over here, no, this person's hydrophobic, they want nothing to do with me. So these water molecules then start becoming more and more restricted, right, in their orientations and their positions that they can dance. So ultimately, you get to a point where the social misfits aggregate, right? They come together, they self-associate, and that will happen, and that is the hydrophobic effect, where you get to a certain concentration of hydrophobic molecules in an aqueous environment, and they come together. Now, you might say, why? Why do they come together? If something comes together, is that an increase or a decrease in entropy? It's a decrease in entropy. Those hydrophobic molecules are more ordered now. They were floating around, now they've come together. But what do we say? We don't be myopic and look at just one thing. We want to look at the system. The system is, even though these molecules have become more ordered, you've caused a lot of the previously stressed out water molecules to suddenly be liberated and be less ordered, right? All these molecules in here are getting trapped, right? We're surrounded by these social misfits, and we can only kind of dance with a limited number of partners. When these guys associate, now everybody is thrown to the outside, so that all of the bad dancers or non-dancers are in the middle of the dance floor, right? And everybody else is around them doing what they did before. So here's an example where you've got a process where part of the system is experiencing a decrease in entropy, more order, but energetically it's offset because many more water molecules that were previously stressed out and limited in their positions and their orientations, they all experience a dramatic increase, right, in disorder, an increase in entropy once these guys have come together, the hydrophobic ones. Do people understand that? Okay? So this hydrophobic effect, it's a driving force for increased solvent entropy. And it's very important in terms of protein folding, membrane formation. We will see how the structure of a membrane and how structures of proteins, their three-dimensional structure, among other things, the hydrophobic effect will contribute to that final structure being formed, okay? Okay, so tomorrow we'll start with acid-base. Hold on one sec. I'll tell you now so that you're not surprised, all right? Tomorrow's lecture dealing with acid-base behavior is very important, right? Acid-base behavior is going to tell you whether or not molecules have charges on them or not, and charges are going to dictate interactions with water in themselves, so you really need to know the stuff for tomorrow.